Hello, everyone. Thank you for joining today's session. We have a very exciting session planned for you guys today. I am Rishabh and I am an applied scientist here at Future AGI. I have worked on building some of the core evaluation components that we have on our platform. And before this, I was at Microsoft working on very similar things. I've built some evaluation frameworks for the co-pilots that we have for Microsoft. With me on call today, we have Alexander. He leads GTM at FriendliAI. Alex has been driving their AI inference solutions to market, bringing valuable experience from scaling AI platforms. And we also have Yan Mo. He's a founding engineer at FriendliAI, and he has been instrumental at building some of the core ML infrastructure that power FriendliAI's inference engine. Thank you both for joining the webinar today, and I'm excited for what we have planned. So today we have an exciting topic. I think all engineers who are working with ML models, they're going to learn a lot from the session. And anyone who is building with Gen AI, I'm sure you'll have a lot to take from. So before I hand over the mic to Alex and Yanmo, just I'd like to set the stage with some context. Today we are going to talk about inference optimization and how it can become a competitive advantage for you or for your business. Now, when we talk about inference, in traditional ML sense, inference is the time that it takes for the model to respond to any query or to any input. But today we are in an era of multi-agentic systems. And when we talk about multi-agentic systems, there are a lot of different components that come into play. There can be certain RAG architectures, there can be many tool calls that are happening within it. And of course, then they are coupled with multiple LLM calls that are happening, maybe for your planning session, for your analyzing session. And all of this takes a lot of time from the time the query comes to the user and to the time they get the response, right? And now I think the users of such architectures, they have become very impatient over time. And now the difference between people from switching to chat gpt to Gemini would be the inference time or the time in which they are getting the response, because quality for now is for a given that both of them are giving a good response, but which is coming with a response much faster. So time now is no more an add-on. Speed has become very important. It's become a feature for a lot of customers that even we are working with, right? They're always very, sensitive about the response time in which the user is seeing a response for their query, right? If we go back 10 to 15 years, if you were watching a YouTube video, often you would see a buffering or a loading sign over there, but that you don't see that anymore, right? So the end users of such, things have become much more impatient. I was reading a report from Amazon that said that if 100 milliseconds increase somewhere in their platform, they can see a 1% drop in their sales. Or for Google search, if there is an increase in 500 milliseconds in their search results, they'll see a 20% drop in the traffic. So it has become very important for us to like show good quality response to the user at a very high speed as well. So that is what we are going to talk about in today's session. Now, as I said, inference time in such multi-agentic architectures can be seen from two levels. One is at the workflow level. So how can you optimize each part of your workflow, such as your RAG architectures, your LLM calls, your tool calls, so that you can get the best response time to the user, coupled with the inference time, the actual inference time that it takes for your LLM models or any other AI model that you're using in the background to come up with a particular response, right? So if you take a deeper look into these multi-agentic architecture, you will start noticing the latency of each of these different components, and that becomes very important when you're trying to debug your system and you're trying to improve on things such as output, but also your latency as well. So at Future AGI, we have built an observability stack that helps you very easily track the latency time of each of these different components, so that you can see what is the input and output for each of these different components and the time as well as the tokens that these different models or components are consuming. Now, to help further with that, we built something known as Agent Compass, which is a zero configuration evaluation system that analyzes the entire trace level inputs that we saw. That is the entire flow that happens from one input to output. It'll take in that entire trace, analyze that, and show you certain evaluations. Of course, qualitative evaluation on the output itself, but also quantitative evaluation. So, for example, if a particular component is taking more time than expected, more time than average, or more time as compared to other architectures out there, it'll highlight those high latency components as well, so that now you can go and then make certain fixes. Or if in your production environment something is taking much more time than it was expected, you can get alerts for those as well, so that you can go and take a look what is happening over there. One thing we have often noticed with developers is that they are often keen on using the best model out there, such as they want to use Gemini 2.5 Pro for everything with the thinking budget on. But what we often suggest is that you might not need such a high-end model for even very basic tasks. So if you want to extract very, specific components of a query that goes as an input to other agents in the system, you might not need a Gemini model with thinking budget on, which is maybe increasing your time it takes to respond to the end user. You might go in with a much smaller model, which is faster in doing these simpler tasks, and leave bigger tasks such as planning to maybe a bigger model, such which maybe takes a bit more time, but gives you more valuable responses. So that is also how you can optimize your workflows to reduce the time that it takes to give a response to the user. We also built something called Fix My Agent, which again takes the entire workflows as input. So if you have built a voice AI agent that calls users and speaks to them, there are different components that goes as input in this system. Maybe a TTS system, maybe a system that transliterates everything. So we go through that entire architecture as well and give you a summary of fixes that you can make in your system. So you can start seeing certain qualitative evals, such as fixing certain memory lapses in your system, or reducing the exposure of PII from your calls. And then also in the architecture as well, which component is taking a lot of time. So for example, if your TTS model is taking a lot of time, we highlight that as well. That might make the agent sound a little less natural. So you can maybe look into the TTS model and maybe use a faster model over there. So we highlight that as well in your Fix My Agent systems. Now, that is one part of the solution, that is optimizing things at a workflow level. But of course, when we are building our own models, fine tuning models, or using certain open source model, the other part of the picture is how do you deploy these models? Because that matters a lot. What kind of GPU infrastructures are you using? Because GPU infrastructure can be very expensive, and often people also do not have the required knowledge on how to deploy them efficiently, such that they can ensure high throughput time, low latency, such that the systems are always up. It becomes very difficult to manage all of these systems, and if you have used certain cloud providers in the past, such as AWS or GCP, you already know how painful it can be to set those things up. So even when we were building our protect model, which is our guard railing systems, we paid a lot of attention in how we were designing these models to have very low inference time, because these are real-time guard railing system, and they have to work with really low latency, so that people can use it in real-time chatbots to intercept certain messages. So we took a lot of care in designing these models, but of course then the other part is deploying them on the right infrastructure as well, such that you can ensure 199% uptime and other things that comes with it. So I think with that, I would like to hand over the mic to Alexander and Campus, because that is where Friendly AI comes in. That is what they have built, a great platform where you can, host your models and then start inferencing on them.
Awesome. Thanks so much, Rochelle. Yeah, and first and foremost, we'd love to just thank the Future AGI team for coordinating the webinar today. And thanks for sharing a little bit about your offering at Future AGI, Rishav. It's really impressive to see the incredible work that you guys are doing to help engineers optimize how they build agents. So really exciting. So thanks so much. So yeah, I think what I can do is what we'd like to do is just kind of give you an overview and an introduction to Friendly AI as we get started. I can share my screen and share a few slides just to provide you some context about what we do as it relates to inference. I can give you a demonstration of our platform as well, of our managed service. And then Yunmo, who's a founding member of our engineering team, will spend some time actually talking about the optimization techniques that we've been able to introduce into our platform to really push the limits on throughput and latency. So yeah, and I think Rishabh, I'm happy to keep this very interactive. So if there are questions that people are asking in the chat throughout the session, please feel free to kind of cut me off and I can jump in and answer the questions right there and then. So and then we'll also spend some time towards the end answering questions as well. Awesome. So let me share my screen.
Sure.
Okay, great. So just as a general introduction to Friendly, we are an inference provider. We're an inference platform. And what we do is really we empower engineers to deploy open source models at scale. And so as some historical context about the founding of our company, we were founded in Korea. Our CEO has been doing research in the GPU optimization and model optimization space for over a decade. And out of Seoul National University, founded a research lab. And in that research lab, they did a lot of experimentation and research on how can you really push the limits of a GPU to drive the performance of language models, Gen AI models. And I think Rashad mentioned this concept of inference being a competitive advantage, right? And I think that's a really interesting way to look at it. As you build Gen AI applications, now that Gen AI is starting to become the preferred methodology by which we interact with applications, I think the optimizing for performance of the underlying model can really differentiate your application from the next, right? And I think Rashad was mentioning, if your model responds faster, if you're building a conversational AI application, that can really make the difference, right? That can really create a very seamless experience for the end user to be able to interact with your application. And that's all powered by, the underlying inference platform, the underlying inference layer. Additionally, the cost effectiveness by which you serve those models is going to impact your company's ability to scale effectively, right? As you onboard additional customers, as you onboard additional users, your ability to scale effectively and not only from an infrastructure perspective, but also from a cost perspective is also going to be in many ways a differentiator over time. So I think this is a really it's a burgeoning space. It's where people are spending a lot of attention on right now because in the past few years we've had a lot of exposure to Gen AI models. Engineers have experimented with them, built prototypes, MVPs, and now they're moving those applications into production where thousands of users are now using your application. And so I think different objectives are now coming into play, right? You're now thinking about how do we optimize this application for performance? How do we optimize this application for cost? How do we optimize this application for scale? And that's exactly what we focus on at Friendly. So as I mentioned, our company was founded in Korea and out of a research lab. And what the team focused on initially was building an inference engine from the ground up. So our inference engine is built from scratch by talented engineers like Yunmo, who have spent their careers doing research on how do you push the limits of a GPU and further optimize it to really enhance how the model performs during runtime. And so Yunmo will spend more time talking about the various techniques that we leverage on an optimization perspective. And I'll just kind of go through the nature of how our platform is structured and how we work with customers. But in essence, like the core technology that we've developed is an inference engine, highly performant. And also, our objective is to, as I mentioned at the beginning, is to make the process of deploying open source models very seamless for engineers and developers who are building Gen AI applications. So we've built a very compelling and effective distribution channel through an integration with Hugging Face. So right now we have the ability to we have support for about 490,000 models that are available on Hugging Face. And developers can easily deploy those those models using our integration with Hugging Face in a matter of a few minutes. And I'll actually run through a demonstration of that later on. So just to kind of share with you the overall structure of how our platform is formed and how we work with customers, we have a few deployment options. The first is a managed service offering where we provide what are called dedicated endpoints and serverless endpoints. So a dedicated endpoint, you would have a dedicated GPU resource specific to your company and your application. And that allows you to, through the integration with Hugging Face, deploy either a fine-tuned model or a model that's a current popular open source model. And we would manage the infrastructure and the serving of that model. And we, in essence, provide you with an API, in essence, to access that model and point traffic to it. And then we also provide a serverless endpoint option, which is, these are basically models that are pre-configured with a shared pool of GPU resources. And we've basically configured about 30 or 40 or so of the more popular open source models that are currently being leveraged by developers on the market today. And in essence, there's a flexibility here. I think dedicated endpoints are specific for certain use cases. Typically, these are for production grade applications where you have some level of predictable traffic that you expect or you're currently serving. And there's also a level of reliability as it relates to a dedicated endpoint. And so, as I mentioned, this concept of us trying to support the scale of your application, we have 4 nines of system uptime, meaning that we have a very reliable system when supporting models being deployed in production. And so dedicated endpoints are the ideal choice for applications that are experiencing predictable and significant volume in a production setting. Whereas a serverless endpoint is very effective as you are building prototypes, MVPs, early versions of your product, and your traffic at this point might be fluctuate and bursty. And so the way that this is structured, our infrastructure scales very well for those types of applications. And this is a cost-effective way as well for you to kind of support those applications. And then the second option of working with us is through a self-hosted option. And this is through our Friendly container. So we have the ability to deploy our inference engine via a Docker container. And that allows customers that are prioritizing security and manage their own GPU infrastructure. That empowers them to basically leverage the performance of our inference engine in their applications that they're building either on-prem or in a private cloud. So those are our 2 kind of deployment options. And I think this flexible deployment option that we provide to our customers allows customers to basically serve multiple use cases that they might have within their organization when building Gen AI applications. We work with many customers that, they have many different use cases for Gen AI. Some of them might be internal facing, some of them might be external facing. And so each one of these deployment options actually can come into play for an organization depending on their needs and depending on kind of the outcomes and objectives that they're trying to drive for that particular application. So just to cover a few of the outcomes that we do drive for customers and kind of what we focus on as being, the unique reasons why a customer would work with us. The first and foremost is the performance of our engine. In line with what Rashad was talking about at the top of the call, we push the performance on the throughput and latency side of things as it relates to the model performance during runtime. On the right-hand side here, you see a chart. This is compared to VLLM, which is a popular open source inference engine. So it's a common engine to benchmark against. So as you can see here, we can drive significant performance improvements on the throughput side of things. This is on a Qwen 3 model, pretty big model, as you can see here, but fairly popular model being used currently today in the market by companies using open source models in their GenAI applications. And we have various levels of quantization, which is an optimization technique that Yunma will cover. And so we have some amazing additional optimization techniques that we layer in to our inference stack that allows us to push the limits, as I mentioned before, on these kind of speed metrics here. Additionally, as I mentioned before, being able to deploy these applications at scale and also cost effectively is something that we're trying to deliver for our customers. And on average, across our customer base, typically when they move to our platform, they see about a 50%, at least a 50% reduction in their GPU spend. And so we're really hyper focused on optimizing GPU utilization, so that way our customers can scale cost effectively. And actually, this is also an effort to make GenAI and the power of GenAI more accessible and more cost effective to all developers out there that are trying to build and deploy applications. And then finally, as I mentioned before, I think reliability is like an incredibly important value that I imagine some of you as engineers are paying attention to as you move a MVP application into production form. Reliability is something that I imagine you're hyper focused on, because especially if your conversational AI application is, for example, serving thousands of your customers, the reliability of that application will impact customer churn. It'll impact user experience, customer satisfaction. And so this is something that we pay a lot of attention to and are hyper focused on because we understand the importance of having your application be reliable. Before I go on to the demo, I'll just quickly share a couple of the customers that we work with. SK Telecom is one of the biggest telecom companies out of Korea. And as you can see here, these are some of the outcomes that we've already discussed before, but these are just in the context of customer relationships. We pushed the limits for SK Telecom on the LLM-based services by 5x compared to what they were doing before, and also generated pretty significant cost savings for them. And then interesting note is that with LG AI Research, we were a day zero launch partner for their XO1 model. And so that's also something to consider. If some of the participants here work for companies that are actually fine-tuning or building your own models and you need a day zero launch partner for that, that's something that we also do and support our customers with in terms of providing them with a distribution channel for their model as soon as it's launched. So I will now move on to like a quick demo of our managed service offering. But before that, maybe we can answer a few questions.
Yeah, we have a couple of questions in the chat. Dhruv is
Perfect.
asking, how can inference optimization become a competitive business advantage?
Yeah, sure. That's a great question. So in line with the themes that we've been discussing, so if you are building, for example, conversational AI application where the core underlying LLM or language model is powering, say, a customer success chatbot, I think the ability for you to serve those customers responses very quickly and responsively and also reliably is going to impact the user experience with your application, right? And so the inference layer controls a lot of that experience in many ways. And so if you have a lot of energy focused on optimizing that layer, I think you'll improve the overall user experience of your application. And therefore, as compared to similar applications that might be on the market, that could be seen as a competitive advantage, right? I think there are many conversational AI applications currently on the market, right? And I think over time, users will probably decide which one they want to leverage based upon the actual user experience, right? Because a lot of them maybe over time have similar functionality. So I'm going to choose the one that I feel is most responsive and has the best user experience. And I think for you on the engineering side that's building that application, for you to be able to move quickly as an engineering team. So time to market is a big piece, right? How quickly can I launch things in my roadmap? And that's another differentiator, right? Competitive advantage in many ways, right? If I know that I can quickly use Friendly AI to deploy new models that are coming out on the market, that allows me to get to market faster, which could also be a competitive advantage. And then finally, the unit economics, improving the unit economics of your application will empower your company to support and scale your application effectively. So I think there's many angles you can take at it in terms of it being a competitive advantage.
Someone has asked, how should one go about choosing between serverless and dedicated endpoints?
Yeah, that's a very good question. I think it has to do with um, the nature of your application in many ways. So, and the stage at which you are in the I guess development lifecycle, right? So, the dedicated endpoints are designed to be reliable and production grade. So, those are typically designed for applications that expect to see significant volume and are deployed in production environments. And then also, I think the predictability of your traffic is also important, right? Because the nuance here is that with a dedicated endpoint, you're actually provisioning specific GPU configuration for your workload. Whereas serverless, that's something that's done automatically from a pool of GPU resources that are actually shared by other customers. So that's the kind of the nuance there in terms of the difference between the offerings on the technical side of things. And so you're also moving from like a time-based pricing model, right? Because you're paying per GPU per hour, and then serverless, you're paying per token, right? So I think it's just a matter of balancing or trying to understand like which option makes more sense at the current moment for the where my application is in like the development lifecycle, and then also like the expected traffic or existing traffic to that application.
And typically, have you seen any like scale of companies that prefer one option over the other?
Yeah, I would say like earlier stage companies typically start off with like a serverless endpoint, and then with like an earlier version of their application, and then as the application scales and reaches a certain level of volume and user adoption, then a dedicated endpoint typically makes more sense.
All right. Last question before we move further. Does Friendly AI support LLM on edge devices?
That's a good question. The way our infrastructure works is that it's cloud based, right? So we have GPUs in the cloud. So on edge, it's not typically an area that we focus on because we typically are optimizing models that are being served by a GPU that's in the cloud. But I don't know if you have any thoughts on this. Like maybe you can answer that question in terms of where if that would be something that we'd be able to help with.
Yeah, to add some more thing on Alex answers. Yeah, so we currently only focus on the like server grade GPU optimization and inference serving on based on the kind of server grade GPU infrastructure. But yeah, I think at some moment we have a very long term milestone regarding the edge device support, but yeah, it's not available at the moment.
Okay, great. I think we can move ahead with the demo.
Okay, great. Awesome. So I'll just do a quick demo and then I'll pass it over to Yumo because I'd love for you guys to listen to Yumo's presentation as well. I think he's got a lot of great things to share. So I'll try to run through this pretty quickly. So in essence, what you're seeing on the screen right now is our friendly suite, we call it. This is where you can get access to serverless endpoints and dedicated endpoints. This is very self-service. It's designed to be user-friendly for any engineer to come on and experiment with models and then also even deploy them into production. So this is something that all of you guys can take advantage of today. You simply just go to friendly.ai/sign up, create an account. You'll get granted access to some credits for you to experiment with. These are our serverless endpoints. So in this case, as I mentioned, these are pre-configured with a pool of GPU resources. These are typically priced on a per token basis or per second basis on how long it takes to produce the response. You can quickly try these models out in a playground environment, and then also get access to the code snippet. This is basically we formatted this in an OpenAI compatible format. So if you're already using this format in your application, it's incredibly simple for you to actually now just start pointing traffic to, for example, GLM 4.6. In this case, you're just in essence changing the model and the base URL, and then you're just getting access to a friendly token in the settings panel of the platform. But once you change those few things in your application, you can actually now start pointing traffic to this endpoint. So again, the objective here is to make this very seamless and easy for you to begin experimenting and also even deploying these models in production. So this is on the serverless side of things. On the dedicated side of things, this is where you would have access to our integration with Hugging Face. So I can create a new endpoint, just call it a test. And through our integration with Hugging Face, I can search for, right now we support over, I think it's about 490,000 models. But here I can, for example, select GPT OSS 20 billion. And then here is where you as a developer will have a few additional customizations that you can tweak for this particular endpoint. So this is where you can select your quantization level that you want to add for this model. Also turn on speculative decoding, which is an additional optimization technique that we can use to push the performance of the model. And then also selecting the GPU resource that you want to leverage. Now, this is going to be workload dependent, right? So depending on your traffic and your volume, this is where you'll select how many GPUs you require. And then once I have this selected, another piece to note is that we do auto scaling. This is actually really important to note. So what this means is, depending if your traffic has like a predictable fluctuation, right? So meaning like say you're a conversational AI that you get most of your requests from 9 a.m. to 5 p.m. at night, right? So you have a pretty predictable level of volume that's happening, and what you can do is basically scale the number of replicas to basically meet the highest point of volume that you'll probably experience in a day. And then our system will automatically scale up and down the number of GPU resources required. And again, this is another cost optimization method that we've built into the platform. And then once you're done configuring, you simply create the endpoint. And once you create the endpoint, what will happen is the GPU will be initialized, the model will be downloaded. And this just takes a couple minutes to do. And then once it's completed, you'll be able to access the code snippet as you were with the serverless endpoint, and then simply replace the endpoint URL and the model name and endpoint ID. And then again, you can start pointing traffic to this endpoint. So this is designed to be very user-friendly, very seamless for a developer to be able to come in, quickly deploy an open source model. And then this is a managed service. So all of the scaling, the infrastructure, it's all managed by our team and optimized by our team. So this is just a quick overview. And as I mentioned, all of you on the call, feel free to go to friendly.ai/signup and start experimenting. And if you have any questions for our team, don't hesitate to reach out. So with that, I'll pass it over to Yunmo. Yunmo has a great presentation on the optimization techniques that we leverage here at Friendly. And feel free to reach out with any questions that you have about getting started.
Yeah. All right. Yeah. So since Alex already introduced our solution and what our mission is, and also Rishabh also covered why inference performance is really important. So I'd like to more focus on the technical side, especially why inference is getting more and more important these days, and how can we improve it by using various inference optimizations. So I think Rishabh already covered this part really well. So inference becomes major bottleneck and more important as various and complex AI agents comes out to the world. And when building AI agents, the model inference is involved in majority of parts of agentic AI workflow. So it is not just a single API call. So for example, the model inference is required to like understand user query and generate multiple tool arguments and parsing the tool outputs, and some components requires another inference to plan the next step or judge the next action. And eventually the another inference is also required to produce the final response. And it means we need lower latency, higher throughput, and cost efficiency in inference, because the agentic AI needs longer session and numerous model calls and tool orchestrations. So, and when we think about the how inference works, the inference itself is very slow and expensive. So because the large model process huge amounts of data, it's auto-regressive step. And these are two phases: prefill, where the input tokens are processed in parallel, and decoding step, where tokens are generated one by one using stored KB cache. So without any special optimization, the model generates one token at a time, and each token requires a full forward pass through the model's billions or trillions of parameters. So these days, as many of you already know, the DeepSync model or some models like Kimi K2, it has like a trillion scale parameters. And these days, some models that has some more complex architecture, like that use linear attention together along with the traditional general transformer architecture. So the things becomes more and more complex, and the optimization itself becomes more and more difficult. So what we want to achieve in terms of the inference is, so we want to keep the model quality as is, and we want to get the lower latency and higher throughput. And to achieve this, we can think about various kind of optimization. So yeah, this slide lists several techniques to optimize each aspect of inference, such as batching, quantization, counter optimization, and etc. So I will walk through details for some of these techniques very soon. So, but the reality is, as a developer and founders, most of us don't want to spend all our time for tuning this kind of low-level infrastructure stuff. So what we want to do is we just want to focusing on developing our own AI services, and we want to make it fast, efficient, and reliable without concerning about this kind of low-level infrastructure matters. So this is what Friendly AI take care of, and what our inference engine, Friendly Engine, does. So yeah, we optimize the inference by retaining model quality, and we optimize the inference by considering the trade-offs between latency, throughput, and cost in the context of various different application scenarios. And we try to deliver the best option for complex optimization spaces. So let's start by understanding about batching. So the techniques that I will cover through this session is kind of fundamental and basics for the ML system engineers, especially the AI inference engineers. But I want to give you a high-level overview and what the optimization knobs to be considered to make the inference better. So yeah, so let's start by the batching. So this is the core strategy for optimizing LLM inference. So when we run inference on GPUs, we are dealing with two types of input data. So first thing is the model weights, which are shared across all requests. And the second one is the activation, which are unique and computed for each different user request. So, and by grouping multiple requests together, we can reduce memory access per request, because we do not need to access the GPU memory or model weights for every single request. And this helps us the memory bound workload into compute bound workload. So to efficiently batch requests, continuous batching is widely used. And this technique was first introduced by the paper named Orca, and it was published by Friendly AI team 2022. And yeah, actually, this was the point about 2021. It was the point when we started to build our own inference engine from the scratch. And it was way before the ChatGPT comes out to the world, and famous open source inference engine like VLM, SGLang, TensorRT-LM exists. So we are pretty pioneer in the space. And anyway, yeah. So yeah, and this continuous batching is an industry standard for many different inference engines that I mentioned so far. And traditional batching techniques like static or dynamic batching often struggle with real-world latency issues, particularly when some request finishes early and another request arrive in the middle of their inference. And continuous batching solve this by continuously rebatching active requests at each decoding iteration. So this one has some great visual demonstration between two different approaches. So this demonstrates the conventional batching. So in the case of this case, it groups multiple requests together into a single batch before processing, and the system waits for the full batch to be ready and then process all requests as a unit. So after a batch is started, a new request join until the entire batch finishes. So, and when we move to the this continuous batching, it continuously fills the processing batch as work completes, and new requests enter the new batch whenever there's available capacity. So it means it doesn't wait for the whole batch to finish so that it can maximize the overall GPU utilization. So next, I'd like to talk about quantization. So this is the technique for accelerating inference by reducing the precision of data and computation. So idea itself is very simple. So using fewer bits per number. So the number means it can be a like weight, or it can be a activation, or sometimes it can be the KB cache. And it means less memory bandwidth usage and lower latency and higher throughput in terms of the flops. But to apply quantization effectively, we need to decide which part of the model to quantize, like, as I mentioned, weight, activation, or KB cache, and which operation to be quantized, such as matrix multiplication or attention. And lastly, we also need to choose which numerical format precision to use. For example, there are like int8, epi8, epi4, and it depending on the hardware architecture, there are some different precision that we can leverage. So, and one thing I want to note is when someone say some inference provider or some inference engine says we use epi4 or epi8, and it does not mean every company or solution use the same method. So in fact, we developed our own custom 4-bit or 8-bit quantization scheme tailored for each hardware architecture, and we carefully balance the model quality and the performance. So that's the key point. And let's also talk about the GPU kernel optimization. So in our inference engine, Friendly Engine, we have our own GPU CUDA kernel libraries, and running LLM inference efficiently. So running LLM efficiently, so it doesn't just about the raw computation. So it's about how well we orchestrate the GPU pipelines. So, and these pipelines are managed at the software level, and without carefully scheduling, we waste potential GPU computation or networking resources by stalling computation or memory units. And the goal is to overlap operations across tensor cores, CUDA cores, or memory passes. And for example, tools like flash attention do exactly these. And yeah, it can reduce memory bottlenecks and keep all GPU parts busy, and leading to faster, more efficient inference. And as I mentioned, at FriendliAI, we have our own GPU kernel library, and we call it Friendly DNN. And yeah, we try to fully leverage the potential of hardware accelerators, considering their characteristic of each of different hardware architecture, model architecture, and inference characteristics. And I'd like to also talk about the KB cache. It is a very critical point for the fast LM inference. So it stores key and value tensors from previous tokens. So during the generation, we don't have to recompute them at every different step. So within a single request, the cache lets us reuse the past context and across multiple different requests. If the same input is seen again, we can even skip the prefill phase entirely. But KB cache consumes lots of memory, and often it takes more memory spaces than the model weights or activation. And we tackle this problem by supporting off GPU caching, the offload the GPU KB cache to non-GPU memory, and utilizing CPU memory or disk spaces. And when we are handling the multimodal data, we need more things to consider, and we are handling those things very well as well. And we need the things like cache or routing in the multi-replica scenario to optimize memory use. Anyway, efficient KB cache usage is one of the best way to reduce latency and memory pressure, especially at scale. Speculative decoding. This is one of the most important technique to reduce the TPOT, time per output token, which means overall generation speed. And this is done by predicting multiple tokens at once instead of one by one in an autoregressive generation cycle. So it uses a small draft model or sometimes some auxiliary layers attached to the target model to generate a chunk of tokens quickly, and then a larger target model, the original model that we want to using. The target model verifies the speculated draft token in parallel. So if the draft tokens match, then they are accepted, and computation for those tokens can be skipped. So, and if it's not matched and rejected, we fall back and regenerate. And as I mentioned, this technique reduced the TPOT very well, but it costs some. It can harm the throughput at some point. So because some tokens may be rejected if the speculation quality is not that good. And what I want to mention is we've developed our own speculative decoding mechanism. We call it Swift. So there's two different regime in the speculative decoding. One is the model-based speculator, which use the draft model, and another one is model-based speculator, which leverage some pattern in the prompt or previously generated output without using the kind of trained draft model. And we have our own speculative decoding speculator algorithm or scheme for each of these regime. And we also have a technique that adaptively exploit both the strengths of both sides, considering the input characteristic. And we also have some technique like self-evolving speculative decoding. So as the inference engine gets more and more requests, the quality of the speculation is enhanced, and it can be the speculation, the acceptance ranks becomes getting better and better as the inference goes on. And lastly, I want to mention the parallelism. So these days, a lot of parallelism exists, but the most generally considered ones are these three. So one is the tensor parallelism. So it shares the model weights across multiple GPUs, and every GPUs are involved in processing each request together, and it requires a collective communication. So it is good for latency, but the trade-off is it is somewhat bad for the throughput compared to other parallelism techniques. Another thing is the expert parallelism. So this can be used for the MOE models, which routes and it routes the request to a specific expert. And each experts are distributed across different GPUs. And and it is somewhat between the tensor parallelism and data parallelism, and it shows the medium latency and medium throughput depending on the cases. And another one is the data parallelism. So in this case, whole model weights are shared across GPUs, and each GPU has the full model weights. And sometimes it can be not just a single GPU, and we can mix the tensor parallelism and data parallelism together. So anyway, it processes the subset of requests, and so each GPU or each replica process different user requests. And it is good for throughput, but it is somewhat bad for latency compared to the others. So actually there is some more thing I want to mention, but considering the time restriction, I just want to end up here. And so far I've introduced some techniques and how they affect the inference performance, and everything we cover so far all comes together in our own inference runtime, Friendly engine. And we built this inference engine designed from the scratch and to handle the demands of various Gen AI workload. So Alex also already shared the performance benchmarking results. So I think I can end up here.
Thanks, Yan.
If there's any question, I think I can answer it.
So there are a lot of questions in the chat. One is, what is the tech stack for the inference engine? I think you already covered it in your presentation. Anything you would like to add?
Tech stack. So it is something like, so we build our engine on C++ and CUDA layer, but it is something like building some framework. So you can think of it like building the things like VLM, SGLang, or like some ML project like PyTorch, TensorFlow from the scratch.
Sonia is asking, do you host diffusion LLMs as well?
Yeah, so our inference engine can support the flux or stable diffusion, diffusion architecture as well.
Puneet is asking, how is the support with accessing via port key or light LLM or any other gateway?
Yeah, so when you're building the kind of building a AI agent using the kind of tools like light LLM, LangChain, or Vercel AI SDK for the JS TypeScript developers. We already have lots of integration with the kind of popular platform. So you can search the documentation our documentation have some tutorial guides on how to use our inference stack with the kind of popular AI agent framework.
Okay. Jyoti has asked, where can I find the pricing?
So the pricing is on our website. So probably the URL is friendly.ai/pricing probably. And it will show you the different pricing for all the product that Alex introduced, the serverless endpoint, dedicated endpoint, and container. And the pricing can be different according to if you reserve some instances or making some kind of contract.
Okay. Do you provide servers in Europe? What about GDPR compliance?
So in the case of the dedicated endpoint, we can, if the customer so we majorly, by default, we try to allocate the GPU resources on the US region. But if the customer has some specific preference on the kind of the region matters, then we can definitely work together, and also we can handle the GDPR compliance together. But in the case if someone need the kind of requirements, it is encouraged to contact our GTM team to discuss further.
There are a few more questions in the chat. Is it okay if we extend a couple of minutes?
Mhm.
Okay. How does auto scaling account for unpredictable spikes in requests?
So yeah, auto scaling, it is also kind of technique and very important to tune the auto scaling policy. So yeah, so the traffic is not stable. So our actual customer also does not have the always stable traffic. So sometimes it is very low and it is very surges at the moment. And we have our own auto scaling policy that we tune based on our experience with each customer. And yeah, and we systematically we try to we implemented various different kind of infra optimization to reduce the cold start latency and make the loading the model weight more efficiently and make so that making our the endpoints up and running much faster. So I think it is one of the most important things to consider for every infrastructure engineer these days who's handling this kind of inference serving matters.
Do the inference techniques change for different models, or are they model agnostic? Does the number of parameters matter?
So overall, inference technique that I introduced so far, this is the common technique, and these are I can say these are model agnostic. But when I talk about something like kernel optimization, GPU kernel optimization, which and each different model uses different different mathematical operations. And to perform that operation efficiently, we need to consider the characteristic of that operation and also the characteristic of the hardware architecture. So it requires some additional engineering and additional things to consider to make the better corners. And yeah, and of course, yeah, some we can we need to implement some different optimization for different models, but yeah, but the things like parallelism, batching, caching, like quantization, spec decoding, those are the common things that can be applied across all different models.
Okay. We'll take last couple of questions. Are friendly AI's GPU libraries faster than NVIDIA's GPU libraries, or does it sit on top of NVIDIA's libraries?
So when you talk about the GPU library, so when we implement our CUDA corners, we of course try to leverage the NVIDIA's very low level library like a CUTLAS or like cuDNN sometimes. But if the reason why we manage our own CUDA corner library is for most of cases, considering so I mentioned that um, AI inference for its model requires some different optimization for each model and its different scenario, and our own developed CUDA corners performs better than NVIDIA's one, and sometimes NVIDIA's corner library does not support every different operation that we need. So yeah, that's the reason why we want to maintain and keep developing our own inference the corner libraries. And if you're talking about if you mean by the like our does friendly engine performs better than the NVIDIA's inference engine like TensorRT LLM, then the answer would be like yes. So yeah, we are internally managing different benchmark for the open source based inference engine like SGLang, BLM, or TensorRT LLMs. And yeah, and most of the different models, the popular models that we run in the benchmark, our engine performs better than any other inference engine across various different workload and different models.
So last question, and I'm also personally interested in this question. Are you planning to extend your support to other modalities such as image, video, audio models as well?
Oh, we already support those different modalities. So image understanding, image generation, video understanding, and TTS, STT. Yeah, we already work with various model provider and companies that using that kind of multimodal inference.
All right. Awesome. I think that is it for today. Thank you, Yanmo. Thank you, Alexander. I think it was a great session. I liked seeing the platform and how easy it has been to like deploy models on the platform. And thank you, Yanmo, for the deep dive into the technical discussion. I really enjoyed it. Thank you everyone for joining the session today. We'll keep planning more sessions, so keep a look in your email for further sessions that are coming.
Thank you, everyone.